In our DC circuit analysis, we found that using the Thevenin equivalent circuit could simplify our calculation for the power absorbed by a particular load resistance. And we can use that same concept to determine the average power delivered to a particular load in a steady state sinusoidal circuit. So, if we can simplify a two-terminal network to its Thevenin equivalent, where we have a phasor voltage VTH in series with an impedance ZTH, we can then develop relationships to determine the average power. Now, in our previous lecture, we found that the average power delivered to a generic circuit element was 1/2 the magnitude of the phasor voltage over that element times the magnitude of the phasor current through that element times cosine of the angle of the voltage minus the angle of the current. We are going to be using the rectangular form of our impedance a lot in this derivation, so I'm going to review that briefly with you all. On a complex plane, an impedance, which is a complex number, looks something like this. Generically, here's our impedance Z, where the projection onto the real axis is the resistance, the projection onto the imaginary axis is the reactance. We have some angle, theta Z. And what's important to realize here is that theta Z is simply theta V minus theta I. Because by definition, impedance is the ratio of the phasor voltage to the phasor current, which is the magnitude of the voltage divided by the magnitude of the current with an angle of theta V minus theta I. So we're going to be using this relationship in a bit, and we're going to be using this form throughout to help us determine how to maximize the average power absorbed by a particular load. All right, so our phasor load voltage VL can be determined using simple voltage division, right? So this voltage VL is the voltage drop over this impedance ZL, so it should be VTH multiplied by ZL divided by ZTH plus ZL using voltage division. Using our rectangular form for our impedances, we find then that this is VTH times RL plus JXL divided by RTH plus JXTH plus RL plus JXL. And we can combine like terms, so we can add the real parts here in the denominator and the imaginary parts in the denominator. And we find that we have RTH plus RL plus J, XTH plus XL in our denominator, and our numerator will stay the same. Hopefully at this point we're comfortable enough with complex numbers that we can figure out what the magnitude of this guy is going to be. So the magnitude of a complex number is a complex number multiplied by its complex conjugate. So we could see from that definition that the magnitude of VL is going to be the magnitude of VTH times RL squared plus XL squared the square root of that quantity divided by RTH plus RL squared plus XTH plus XL squared, and then the square root of our denominator as well. So you may be asking yourself, gosh, why did we bother going through all of this? Well, I'm going to plug this exact relationship in for the magnitude of VL in this expression. Next, let's find our current IL. So IL, we could see just using Ohm's law, is going to be VTH divided by ZTH plus ZL, which is equal to VTH divided by RTH plus RL plus J XTH plus XL. So if our denominator here equaled that, then this same denominator should show up there. And we can see then that our magnitude of IL is going to be the magnitude of our Thevenin voltage divided by RTH plus RL squared plus XTH plus XL squared, and this whole guy square rooted. Now the last bit may be slightly harder for you all to see. So I'm going to put my rectangular representation of an impedance back on the board here. So this is R on the real axis, X on the imaginary axis, and this is theta Z, which again is equal to theta V minus theta I. So cosine function, by definition, is the adjacent divided by the hypotenuse, where the hypotenuse in this case is R squared plus X squared square root, using good old Pythagorean theorem. So we can see that cosine theta VL minus theta IL is R divided by the square root of RL squared plus XL squared. And actually, I'm going to do this, I'm going to write it slightly different, to the 1/2 power. Oh, and this should be RL here. So, what's going to happen now that I have all three of these constituent parts? Well, let's find out, shall we? My average power is going to be 1/2 times the magnitude of our phasor voltage. So this is RTH plus RL squared plus XTH plus XL squared to the 1/2 power. VTH RL squared plus XL squared to the 1/2 power. When I put in IL, I'm going to get this same denominator here, RTH plus RL squared, XTH plus XL squared to the square root, magnitude of VTH in my numerator, close that guy off. And lastly, I'm substituting in my relationship for the cosine. So that's going to give me an RL squared plus XL squared to the 1/2 power. And up here, I'm going to have RL. So, first things that we can see is that this guy and this guy cancel each other out. And this denominator multiplied by this denominator is going to get rid of those square root signs. So that I will have 1/2 times RTH plus RL quantity squared plus XTH plus XL quantity squared in my denominator. And in my numerator, I'm going to have the magnitude of the Thevenin voltage squared multiplied by RL. So we've done a lot of work to get to this point. Let's talk about how or why this is useful. This is our average power delivered to our load. So if we know the rectangular and form of our Thevenin impedance and the rectangular form of our load, as well as just the magnitude of the Thevenin voltage, we can get a numerical answer for the average power, no problem. This is also going to help us maximize our relationship. And so what I mean by that is we can observe that the reactive portion, or the reactance portion of our impedance, it does absolutely nothing to make our average power increase. So we will have a maximum average power, so P average max depends on XTH being equal to negative XL. Or I guess a better way to put this would be XL, the reactance of our load, needs to be negative of our Thevenin reactance. Because if this doesn't occur, we just have a term that's in the denominator, which is by definition making the denominator larger and therefore making the average power smaller. Now, under the assumption that this is true, our average power reduces to 1/2 times RTH plus RL, Yeah, no, that was right. RTH plus RL squared divided by the magnitude of our Thevenin voltage times RL. Now, this may not look familiar to you, but this is actually, except for this factor of 1/2, the exact same expression that we maximized in our DC maximum power transfer theorem. For that case, we found that maximum power transfer occurred whenever RL was exactly equal to RTH. Since we're maximizing the same equation, we can get to that assumption as well. So P average maximum depends on RL being exactly equal to RTH. With both of these two constraints combined, we find that maximum average power transfer occurs in a steady state sinusoidal circuit when ZL, the impedance of our load, is equal to the complex conjugate of ZTH, which by definition is R minus J, or RTH minus J XTH. So under this specific condition, maximum average power transfer occurs. Our relationship for maximum average power transfer then becomes P average max is equal to 1/8 the magnitude of the Thevenin voltage squared divided by the Thevenin resistance, which is the real portion of the Thevenin impedance. So it's the exact same result that we got for a DC circuit, except multiplied by this factor of 1/2. Alrighty, thank you guys for watching.